Thanks, guys, for joining. Good afternoon, everyone. My name is Imam. I'm Manager Technical Marketing, leading the Catalyst Switching TME team. I've been with Cisco for about 9 years now. I've been working on the Catalyst Switching portfolio for about 5 years, since the very early days of the Catalyst 3850s and the UADP ASIC, and have been working closely with the engineering teams, engineers like Peter Jones and many others, to understand the platform architecture, to understand the ASIC architecture, and how it can benefit our customers. Now, Cisco has been at the forefront of innovation in the ASIC areas, and we have been building our own custom ASICs for years now. And it has been a pillar of Cisco innovation, the ASICs. Traditionally, though, when we talk about the ASIC, we assume that the ASICs are purpose-built, fixed ASIC. And what that means is every ASIC has some kind of processes to do and some kind of pipeline, a parser. Traditionally, these parsers have been fixed. The pipelines have been very, very fixed. That means that if it is designed to process an IP packet, or IPv4 packet, let's take an example of an IPv4 packet here, it will be only able to process an IPv4 packet. If it is not designed for IPv6, it won't be able to process the IPv6 packets, right? Tomorrow, if there's a new innovation, a new technology coming out with new type of headers or new type of encapsulations, this ASIC won't be able to handle that, right? Because guess what? What we have to do here is we have to insert different things in the pipeline to understand that packet and then process it. So let's take an example. So these are the different type of lookups that can be done, for example, on this ASIC. If VXLAN comes out as a new technology, right? Or if you want to implement an older technology like GRE or MPLS on a switching platform or on a platform which was not supposed to do MPLS and GRE, now we are looking at basically a new ASIC, right? And you will hear things like not supported in hardware. And you guys probably know what that means. That means whatever you can do in the software, great, you can do it in the software, but the hardware is not capable of. So what that means that you have to go and build a new ASIC, right? That's great. The problem is the ASIC, from the day it starts, from the marketing requirements, building the architecture, doing the design, synthesis, floor planning, fabrication, and all the way until you get the end product, which looks something like this ASIC here, it takes 2 to 4 years, right? That's a pretty long time. So if a technology comes out today, in 2017, you have to wait until 2020, 2021, potentially, to have that technology implemented in a product. By the way, Dave Zach has talked to some of you guys, I think, last year here in Berlin, and went through a lot of details on how ASICs are built. So I'm not going to go into the details of those here. So building a new ASIC takes a lot of time. What we have done in 2013 is Cisco has introduced a new switch called 3850. This 3850 is built on an ASIC called UADP ASIC, or Unified Access Data Plane ASIC. This is a new innovation in the ASIC technology because this is slightly different than the traditional ASICs that we used to have. This has programmable pipelines. This has programmable stages of the programmable pipeline that can be programmed in different ways, very different than what we used to have traditionally. So in 3750X, for example, in the 1960s, which used to use Strider, Sasquatch ASICs, those were fixed ASICs. UADP ASIC is more flexible, more programmable. Okay. So in the next 15-20 minutes, what we are going to do is we are going to look at 3 key functionalities of the UADP ASIC. The first one here is flex parser and programmable pipeline. Okay. This is a quick block diagram of the UADP ASIC. If you look at the UADP ASIC, we have the network interfaces connected here on the left side, right? We have the stack interface on the other side. So your traffic is coming in from the front panel ports on the left. It could go to other ASIC potentially on the same box or on a different box in a stack environment through the stack interface. And between these two interfaces, we have a bunch of different components. The first one here is ingress FIFO. So when the packet comes in, it goes through the ingress FIFO for brief queuing. It's just a small one. And then the packet is played out to two different components. One of them goes to the ingress forwarding controller, and the other one goes to the packet buffer. The one that goes to the packet buffer, it sits there and waits for instructions, right? While the other packet that goes to the ingress forwarding controller is the packet that actually gets processed. Then we have different types of queues. Here's the ingress queue scheduler that takes the packet to the stack interface. We have the egress queue scheduler with multiple level of queuing that takes the packet back into this block that we'll talk in more detail a little later. Then we have the rewrite block and the egress FIFO, which takes basically the packet out to the egress interface. Now this one here, this big block, this is kind of the heart of the ASIC, right? The key processing and the main processing of the packet actually happens here. So what I'm going to do here, I'm going to open this heart a little bit more and show you what's inside. Okay. So if I take the covers out, you'll see something like this. And that's where we have the programmable pipeline. That's where we have the SRAM, TCAM, some of the fast storage memories. So let's expand this a little bit more. Okay. So I'm expanding the last middle picture, making it slightly bigger so that we can read. When the packet comes in, remember one packet is sitting in the packet buffer. The second packet is going into this pipeline. We take that whole packet and we parse it. We parse the first 256 bytes of the packet. Okay. We throw the rest of the packets away. That first 256 bytes of packet is where we have most of the information that's relevant to us, right?
So you could parse extension headers or what have you down to 256 bytes.
Correct. Yes, absolutely. Then we take that 256 bytes of the packet and we take them through multiple different stages. At each stage, you can do an action and you can do a lookup to one of these memories here, right? So you look up what kind of packet it is, L2, L3. If I want to do an L2 lookup, which table I need to look at. Okay, so the packet goes through the different stages. We have 15 different stages in the UADP ASIC.
And you can program them to do whatever you wish.
Exactly. We can program each stage different way. Okay. Now, here in the middle, you are seeing these lookup tables. These consist of TCAM and SRAM, right? So in the Catalyst 3850, we have about 12,000 TCAM entries. And then we have multiple features using the SRAM with different capacities. Similarly, on the egress side, we have similar stages. However, on the egress side, we have only 7 stages. Because most of the processing tend to happen, most of the lookups tend to be in the ingress side of the pipeline, right? And then
now that you went into TCAM and SRAM, I mean, you brought this up. What do you store in TCAM? What do you store in SRAM?
Yes, we are going to talk about it. I have a slide there. So TCAM is usually used for ACLs, QoS. SRAM is used for lookups like fib, where you have the routing entries, longest prefix matches, and so on. So I have a slide. We are not going to go into too much detail, but we'll touch on that.
I have a question from the slide before, if you can go back one. What is the reassembly doing there?
Yes, that's a very important question. I'm going to talk about it in the recirculation. So I'm going to touch on that as well. Okay? All right. The last couple things I want to mention on this slide is the IGR and the EGR. These are the decision makers. Okay? Because the packet goes through all these different stages. At each stage, there could be different decision. Maybe a policer says, drop this packet. Maybe an L2 lookup says, forward this packet. So those decisions are being kept in the packet descriptor that we have. And the packet descriptor will take all these different decisions to the IGR. And the IGR then will decide what to do with this packet. Now remember, the actual packet, the entire packet is sitting in the packet buffer. So the packet descriptor will go to that packet, will get attached to that, and then the whole packet starts to move from that point onwards. Okay? Now, here is a quick look of some of the actual stages on the Catalyst 3850. This is not a comprehensive look. It's more of a simplistic look of the Catalyst 3850. So you can see here we have L3 lookup, L2 lookup happening in one stage. At each stage, we can have up to 2 lookups. Okay? We can also have a stage without any lookups if needed. So we don't really have to use all the 15 stages. Similarly, on the egress side, we can do 2 lookups per stage. Okay? Now, the question here is, how do we program these stages, right? That's where we have something called microcode. Okay? Microcode is the layer of code that sits very close to the ASIC, right next to the ASIC. And then on top of the microcode, we have the different software features like OSPF, MPLS, ACL, COS, all of those different features that the users can actually use that are sitting on top of the microcode. When we want to enable a new feature, right, like VXLAN, for example, we go and program the microcode so that it can handle that packet in the programmable pipeline. Okay? And so when we introduced Campus Fabric, for example, we have added this capability, right? We have also added the capability of MPLS in Catalyst 3850, right? All of this has happened after we have launched the Catalyst 3850 about more than 4 years ago, right? And that's where we have the power of the programmability in the ASIC. Now, the other key functionality that we have is the recirculation, right? So if you go back to this block diagram, right? Somebody mentioned here what do we have here? This is the recirculation block, okay? When packet comes all the way through all of these processing, goes to the egress forwarding controller, to the rewrite block, at that point, we determine if the packet needs to be recirculated. There are certain cases where packets needs to be recirculated. For example, if packet needs to be reassembled, if packet needs to be encapsulated or decapsulated. In all of these cases, what happens is you end up with a new set of headers after the encapsulation or decapsulation. Now, those new set of headers that you have to put it back into the pipeline so that we can do the lookups one more time, right? Yes?
Some vendors do that by having internal loopback interfaces. which limits the bandwidth of recirculation. Do you have a similar limitation, or is it at full performance of the switch?
Okay, so the question is basically what kind of performance compromise we have with recirculation. And that's why we have this slide, I'll come back to here, where I talk about the performance, right? When we, so the total performance of the UADP ASIC is 56 gigabit. This is with 64-byte packet, so this is the worst performance possible. Now, if you look at the platform architecture, you'll see that this ASIC is connected to 24 downlink ports and a 20 gig worth of uplink ports, right? And we reserve 2 gig for CPU. That leaves us with 10 gig of bandwidth. We use this bandwidth for recirculation, okay? Now, since we are on this slide already, let me also point one more thing here. Whenever we talk about recirculation, the one concern I always hear is how about latency? Because we have recirculation bandwidth, so we can go and do the recirculation with still having the switch line rate, right? Because we have additional bandwidth. But each recirculation means more time, right? And so how much time do we take for each recirculation? It's half a microsecond, okay? In Catalyst 3850 and the UADP ASIC, this is meant for campus environment, for enterprise environment. Half a microsecond in that environment is negligible, right? So the point is, with this ASIC, we do have recirculation capability, and we can do up to 16 recirculations. Each recirculation adds half a microsecond. I have not seen any case where we go to all the 16 recirculations. That would be crazy. But we do up to 7 recirculation in certain cases. And yes.
So if you would have to decapsulate VXLAN and then do routing, can you do that in those 16 stages in one pass, or do you have to do recirculation?
Just because we have VXLAN as an encapsulation, we have to do a recirculation for sure, right? So we decapsulate the packet and recirculate. Now let me go back to this slide where I talk about recirculation. So in this example, if we have a encapsulated packet, right, coming in the port, it goes through that IFC, the red box that we saw earlier in the heart of the ASIC. This packet is coming with this bandage thing, which means it's encapsulated. It will go through the IFC. It will do its different lookups. It will do the forwarding lookup. What it's going to determine there is this packet is encapsulated, right? So at the EFC, it is going to decapsulate the packet. Once it's decapsulated, it takes the packet in the recirculation path, right? So it takes this packet through the recirculation path back into the IFC. And now, because we have a new packet header, we'll look at this new packet header one more time, right? We'll apply any policies, and we'll determine the final DI, or the destination interface, right? Apply the necessary egress processing, egress policies. We'll do the final rewrite, and then we will send this packet out. So that's what's going to happen in a recirculation case. This could be multiple. When I say 16, this process could go up to 16 times. Right?
Each time you're dropping the original packet and putting the new one into your packet buffer?
Potentially. In the packet buffer? In the packet buffer, every time it goes through the IFCs, yes, it will put the packet back into the packet buffer. Correct.
So you discard the original one, decapsulate it, or you decapsulate it, discard the original one, and put the new one in there?
Right. So when the packet goes back into the recirculation path, now it has the full packet with the decapsulated headers, right? When it goes to the IFC, it will put the actual packet in the packet buffer and will take another copy of the packet to the IFC. IFC will take the first 256 bytes and throw the rest of the packet away. Same processing will happen again. When it comes back out of the IFC, it will take the packet from the packet buffer, will put the packet descriptor, and then we'll send it back into the EFC. All right. And then the packet goes out with the DI. All right. Now, we talked about this slide earlier. So I'm going to move to the next key thing on the UADP ASIC. One key component here is the micro engines. Okay. So the UADP ASIC, if you look at this block diagram, the micro engines are spread around at different places. Okay. If I take this out, this is simplistic view of the different micro engines that we have. You'll find over a dozen micro engines doing different things. Okay. Now, what are the different micro engines doing here? There are micro engines who are doing the encryption. There are micro engines who are doing fragmentation, reassembly, net flow lookup, policy lookup. Rewrite is also a micro engine. We have different search engines. So we have hash table search engines. We have TCAM search engines. We have the longest prefix match search engines. All these different search engines access the different types of memories that we talked about and do the lookups. Okay. These micro engines are more purpose-built. They are not as programmable as the programmable pipelines that we have. Okay. So these are purpose-built, but these are doing some important functions for the ASIC. Okay. Now, since we have launched Catalyst 3850 in 2013, we have introduced a couple of variations of the UADP ASIC. This is the UADP 1.0, right? Internally, this is called Doppler. It comes with the capability of 1 gig, 10 gig ports. It has 240 gig of stacking capacity, and I'm talking about the real number. We can get up to 480 gig with a spatial reuse. That's more of a marketing number. 128-bit of encryption. It comes with 6 meg of packet buffer. Okay, compare that to the previous generations. You used to have just 2 meg of packet buffer. Each ASIC has 24,000 net flow entries cache capacity, right? And then we talked about the bandwidth. This is the 56 gig. What that means, that gives us a lot of different features that we can do with this ASIC, right? Features like SGT and wireless, CAPWAP, span, and so on. These are some of the versions of the Catalyst 3850 that are using UADP 1.0. Okay. Later, about 2 years back.
Question before you go on, you had only 1G and 10G. The substandards N-base-T are also.
The N-base-T is, okay, so this is 1.0, right? The N-base-T or multi-gigabit switches that we have, they use 1.1. And that's where we have this ASIC. Okay, that's why I'm mentioning this. There are 2 variations of this ASIC. And there are different products which are using the different variations of the ASIC. So 1.1, very similar to 1.0, but on top of that, we have additional functionality. So it does support 40 gig, for example, right? It supports multi-gigabit. It comes with dual core. So each of this ASIC, the one that I'm holding here in my hand here, this is a 1.1. And this has about 3 billion transistors, comes with 2 cores, right? It also, what we have done here is we have also added the IEEE 1588, which helps us with features like AVB and precision time clocking. Each of these cores has 24K 24,000 net flow entries, right? And additional security thing here is we have 256-bit MACsec encryption, right? This is a micro engine in the chip that can do the MACsec, unlike MACsec being done on the PHYs. Okay. Now, what that means, this comes up with a new range of software features that we can do, right? Features like AVB, ERSpan, StackWise Virtual, 40 gig capability, and so on. Now, these are the different switches here. The multi-gigabit switch, SFP plus switches. Then we have the Catalyst 3650 Mini and the 3650 multi-gigabit. All these switches use UADP 1.1. Okay. So the question is, how UADP has helped us and our customers in the last 4 years since we have launched the Catalyst 3850. Okay. So when we introduced Catalyst 3850 in 2013, we had a good amount of features, right? About 80% of the features that we had in 3750 we brought to the 3850. Over time, we have added, I'm only talking about those features that need ASIC changes traditionally, right? That needs programmability at the microcode level. By 2015, we had a lot more features being supported on the Catalyst 3850, things like ERSpan and SGT group and so on, right? And today, we are supporting MPLS. With Campus Fabric, we are supporting VXLAN and Lisp encapsulations. We are supporting ERSpan, we are supporting MACsec 256, and so on. Okay, so we started in 2013 with a small amount of features. With the help of the programmable stages, now we can deliver to the same customers using the same switches that they bought in 2013. They can run that many features.